Before we start this video, let's define what the fourth dimension even is. What we perceive in our everyday life is the third dimension, in which there is the y-axis, which defines up and down, the x-axis, which defines side to side, and the z-axis, which defines forward and backward. But if we add another theoretical axis, the w-axis, we can see the existence of another theoretical plane that we cannot comprehend in our vision of the third dimension. You are now entering the fourth dimension. Now let's say that you have a balloon in the form of a globe, a 3D sphere raised to the fourth dimension, also known as a hypersphere in 4D. You are blowing the balloon up so that after 10 seconds, its 3D surface area is 16 pi centimeters squared. The radius of the balloon is changing at 2 centimeters per second. Find the rate of which the 4D volume of the globe is changing. Here is the function to solve for the surface area of any given sphere, given n dimensions. We want to now solve for the radius, so we need to derive the 3D surface area equation first. To do this, we need to solve for the gamma function of 3 over 2. We can do this by either solving 3 over 2 minus 1 the whole factorial, or using Euler's integral of the second kind, as both should give the same answer. To solve the integral, solve for the indefinite integral first, using integration by parts. After, use U substitution and the Gauss error function to solve for the range from 0 to infinity. In both ways to solve the problem, we get the square root of pi over 2. Now we can plug this into our original equation, which is set to 16 pi as given in the original problem, and we can see that the radius is 2 centimeters at 10 seconds. Now we need to find the volume equation of the hypersphere in the fourth dimension using a similar formula to surface area. By plugging in 4 as n, we need to solve the gamma function for 3. The first method, 3 minus 1 the whole factorial, yields 2. We can solve for the Euler's integral by using integration by parts twice and then use substitution at the end. Again, solving from the range of 0 to infinity, we get 2 as our final answer. We can plug this into the volume equation to get half times pi squared times the radius to the power of 4. With our newfound volume equation, we can solve for dV over dt, or the change of volume with respect to time. We do this by taking the derivative of the equation. We know that the rate of which the radius is changing is 2 centimeters per second. This is also theoretically the surface area of the globe in the fourth dimension times the change in the radius with respect to time. If we plug all of our values in, we can see that the volume is changing at 32 pi squared centimeters to the fourth per second, which is our final answer.